be speaking about the virtually imaged phased array for Brillouin microscopy. I'm Divyendu Valappil, and I'm currently a PhD student with Restore Labs and ONERA. And my PhD topic is Brillouin microscopy to analyze biological samples and aerosols. So what exactly is Brillouin light scattering, which has been used for Brillouin microscopy? So light scattering occurs in two different ways. So you have elastic light scattering or inelastic light scattering. Elastic light scattering is an interaction between photons, and inelastic light scattering is an interaction between photons and phonons. Elastic light scattering, like Rayleigh scattering or Mie scattering, solely depends on light-light interaction, whereas inelastic light scattering, like Raman scattering or Brillouin scattering, depends on light interaction with density fluctuations, which are induced spontaneously. And these are also dependent on temperature. So since there's a dependence of Brillouin light scattering on the phonon velocity, the tissue's elasticity, and also temperature, how we understand the application of Brillouin light scattering is through the Brillouin shift. So Brillouin shift is the distance between the peaks of Brillouin light scattering, which is the Stokes peak or the anti-Stokes peak, and Rayleigh light scattering, which is the elastic form of light scattering. So this Brillouin shift will essentially give you information about tissue mechanical property or information about tissue's viscoelasticity. And that's what we use in Brillouin microscopy. So what is the motivation behind such a project? We know that 3D optical imaging of living organisms is constantly done, and it's done in various ways like light sheet microscopy or confocal microscopy. And these are also used to study the optical and mechanical properties of these complex biological media. But many times what happens is that the samples that you use, all these techniques, or most of the techniques, are quite invasive. So what we are trying to do is to develop a technique by combining advanced imaging techniques like light sheet microscopy and Brillouin microscopy for imaging, for 3D imaging, for 3D non-invasive imaging for heterogeneous samples. Non-invasive is a really important word here, and it's live imaging. So that's what we're trying to do. So this inelastic Brillouin scattering and light sheet microscopy can also be used for interdisciplinary applications, and that's where aerosols come in. So once we have all this in mind, what exactly is the biological context behind using Brillouin microscopy? So you know that elastic vibrational waves cause light to scatter in different ways when it interacts with the solid material. And this different behavior depends on what exactly is the composition of these solid materials. So depending on the composition of the solid materials, there is a difference in the frequency shift. So if you see here, there's a different interaction between these cells, and there's a difference in the frequency shift between the Rayleigh peak and the Brillouin peak. So this is the concept that we effectively use for all of the analysis of Brillouin microscopy. And even though Brillouin microscopy has existed before, it's always taken so much time. So a 2D image takes hours together, and a 3D image takes maybe even 3-4 days. And most of the information that you receive from your images, or because they're not essentially images, they're just light signals which you need to then convert into graphs to understand the frequency shift. So it's just a lot of noise. So you have a very low signal to noise ratio. So what we try to do here is to use a spectrometer to increase the signal to noise ratio and also reduce the time for imaging. So a Brillouin microscope needs a light source, a laser. It also needs an imaging system, which is a high sensitivity camera, and then a spectrometer, which could be a Fabry-Perot interferometer or a tandem Fabry-Perot interferometer or a VIPA, which is the virtually imaged phased array. So there are systems that use more than one VIPA, but the system that I'm developing uses only a singular VIPA. So why do we need a spectrometer for a Brillouin microscope? We know that every substance that is measured is unique and it gives you distinct light patterns, which serve as identifying markers. It can be anything. It can be from water to the most heterogeneous material. So all of it has very, very distinct light patterns that we receive. So this allows the analysis of the substance and it allows us to determine its composition. So when we use this system, when we use a spectrometer, what it essentially does is to try and reduce the information of what we don't want and to increase the effect of what we do want. So that's exactly what it's called as signal to noise ratio. So we are trying to reduce all the unwanted noise and to increase the signal so that we further understand and we better understand what is the composition of the sample. So in the different spectrometers that I introduced, I'm going to give you a short explanation about the Fabry-Perot interferometer because it has been used a lot of times. So a Fabry-Perot interferometer, it's like a linear optical resonator which consists of two highly reflecting mirrors, but this is used as a spectrometer. So these two mirrors are confocal mirrors and they have a distance between them. And you can tune this distance and you can change the resonance frequency by tuning the distance of these two mirrors, which means that the Fabry-Perot interferometer has moving parts. Now coming to the VIPA or the virtually imaged phased array. A VIPA is a special type of Fabry-Perot and it's an etalon, which is a glass piece, but it has three distinct coatings on this piece of glass. So one surface of the VIPA has an anti-reflection coated section, and adjacent to this, you have a highly reflected surface, and opposite to this, you have a partially transmitting mirror. So you have one surface which is highly reflective, one surface which is anti-reflective, and one surface which is a partially reflective surface. And this is a solid piece of glass. So that's why it's called a VIPA solid etalon. So it's a solid piece of glass which looks like this. And the light is introduced through this AR surface or the anti-reflective surface. And I will be explaining what exactly happens once light is introduced into that area. So there are different parameters that you have to keep in mind before you choose a VIPA for your system. You have to understand that the optical thickness of this VIPA cannot be changed. So once you choose your VIPA, because it has no moving parts, your optical thickness has to be decided before you choose your final VIPA, before you choose one to buy for your system. And the second is the reflectance of the output mirror. So the partially reflective coating. So this is the second factor that defines your performance of the VIPA. So in principle, a higher reflectance mirror will increase the resolving power, but you also have to keep in mind that there needs to be a significant difference between this high reflective coating and a partially reflective coating. It cannot be 100% because the idea of the virtually image phased array is then lost. And third, you have the internal angle of the light traveling through the VIPA. So once light is introduced through the anti-reflective coating, there's an angle at which it travels through the VIPA. And smaller angles definitely increase the angular dispersion, but there are factors that put a lower limit on this angle. And I will be coming to that later when I specifically talk about my system. And the VIPA coatings that you select need to match the wavelength range that you're using, and the material must be transparent. Keeping all this in mind, thanks to RTM-FM, we have a VIPA from Light Machinery, which this is exactly the VIPA that I'm using for my system. Thanks to RTM-FM, this was bought from Light Machinery. The material is fused silica and has a really good surface quality, which tends to 5. But if you see this VIPA, you know that it's very small. The dimensions are just 22 by 24 millimeters and a 3 millimeter input window. So this tiny window notch that you see here is the 3 millimeter input window. So why do we use a VIPA and why not use a Fabry-Perot system? So VIPA is essentially a further improved version of the Fabry-Perot because you do not have moving parts. So in a Fabry-Perot, you have two mirrors which can be moved. The distance between them can be changed. But for the VIPA, you do not have that, which makes it more stable. And also it has the function of dispersing the spectra in space, and it doesn't really require that optical cavity which a Fabry-Perot interferometer has. And second, the resolving power or the reflectivity of the back surface of the VIPA is dependent on the thickness, and it's dependent on the material used. So that's something that you can choose based on your system. And it also provides you a sufficiently large angular dispersion, which separates the Brillouin-Stokes and anti-Stokes peak, so which is what you want in your system. So the VIPA is definitely an easier solution than the Fabry-Perot. So what happens in a VIPA is that you have an incident beam which goes through the anti-reflective coating surface, and it has multiple reflections inside the glass echelon. And what you get behind this partially reflective coating is a virtual image. It's an array of light with a decreasing intensity from bottom to top. So the bottommost has the highest intensity, and then you have decreasing intensity to the top. So step 3, how do I align a VIPA? Now that I have my, I understand that I'm going to build a Brillouin microscope for biological samples, and I have chosen my VIPA. How do I align the system? So this system that I use to align is one of the most simple systems that you can use, but it has absolutely nothing to do with my final optical design. So I have a laser source, then I have mirrors for ease of changing the slightly changing the angle or slightly changing the height of my signal. And then I have a cylindrical lens before the VIPA. And then I have a spherical lens after the VIPA. And finally, I have the camera. So what you see here in my system are screws that I can use to change the direction and the height and the lateral direction of the VIPA. So there are 3 degrees of freedom here. So this one changes my height, this one changes my angle, and this one also changes my angle or makes it orthogonal. I also have a system here which can be used to change the distance between the cylindrical lens and the VIPA. But the problem that we face here with using a cylindrical lens and VIPA system is that the cylindrical lens orientation also depends on the VIPA's orientation, or the VIPA's orientation depends on the cylindrical lens's orientation. It happens vice versa. So the system that I've used here is what you see in this figure. So all of this is taken from a paper by Zhitao Zhang. And he has used a system which has two VIPAs, but my system has only a singular VIPA, and I have chosen VIPA 1 and C1 configuration. Because when you try and align the system with a cylindrical lens, it's definitely easier when your height is set. So you know that your signal has to go through the middle of your cylindrical lens, and then you can align it to the bottom of your VIPA, rather than having a system which is going to has to go through the middle of the cylindrical lens in a longitudinal fashion. So we chose the first system with VIPA 1 and cylindrical lens 1. So when you align the VIPA, if you have it orthogonally aligned with your cylindrical lens, what you see is a dot. So it's a perfectly aligned laser system. But what you need is an array of light. So we changed the angle by 1 degree. And how we change the angle by 1 degree is using these screws. So we already know that 1 turn of the screw is going to be a certain value based on the system that you use. And then we calculate it to be 1 degree. Essentially, for the best output, it should be 0.87 degrees. But since with my system, the minimum that I can accurately calculate for the angular difference is 1 degree, I've chosen to do it as 1 degree. And once I change it by 1 degree, I have a varying intensity, as you see here, with a maximum at the bottom and minimum at the top. And this was done in collaboration with University of Montpellier, thanks to Alban, because the alignment of a VIPA, when it was done at University of Montpellier, because they did it in the beginning and they did it on their own. So it took them more than a year. And because we had some help, it still took us 3 to 4 months. So that just shows how complicated it is to align the VIPA. So once we have the VIPA aligned, once we have the virtually image phased array, which is a spectrometer aligned, how am I going to get the spectrum? If you see this figure right here, you see that you have a reflective surface, which is 100% reflectivity, and then you have 95% reflectivity. And you have an incident beam going through the anti-reflective surface, which has multiple reflections through the glass echelon. And this virtual image is collected using a cylindrical lens. And finally, it is taken to the CCD camera or any camera. So it can be a CMOS camera, any high sensitivity camera. So once it goes to the camera, the image that you see is actually just lines or points. If you use one single VIPA, you will be seeing lines. Your spectrum will be lines. So in the lines, you have Rayleigh scattering, and on either side, you will have Brillouin scattering Stokes and Brillouin scattering anti-Stokes. But if you use a 2 VIPA system, as seen here by Zhitao Zhang, what you will be receiving is points. So you will get points of Rayleigh peaks and points of Brillouin peaks. But what we need to understand here is, even though we use the virtually image phased array, it is quite difficult to distinguish between a Rayleigh peak and the Brillouin peak, because the Rayleigh peak, which is elastically scattered light, is very, very dominant. It's bright, it's easily visible, and it's super dominant. And the Brillouin peak, this is an image which is quite animated, because the Brillouin peak is not going to be so high. It's going to be very, very small, very minute, something that you see here in this red figure. Even this is quite animated. What you're going to see is much smaller. So that is why we need to use a spectrometer. If we didn't use a spectrometer, it would be practically impossible to see any difference between the Rayleigh peak and the Brillouin peak. So that's where the spectrometer is necessary to get a difference between the Rayleigh and the Brillouin peak. And then once we have the distance between the Rayleigh and Brillouin peak, we have our frequency shift. And this frequency shift can be used to understand the mechanical properties of your sample, to understand the viscoelasticity of the sample. Thank you very much, and I will be taking questions.